In this video, we'll discuss the Heisenberg uncertainty principle, look at some details of orbitals, and discuss the fourth quantum number spin. So one of the consequences of quantum theory is this Heisenberg uncertainty principle. And we can think about an experiment for this. So let's say we're trying to measure the position and momentum of a tennis ball. So something that is large. And we know we can do this all the time if the tennis ball is bouncing. So basically the ball is moving. The light reflects off the tennis ball. It doesn't change the direction the ball is traveling. And so we can see the light, see where the ball is going, and know which direction the tennis ball is moving and where it is. So we can know both of its position and its momentum. Its momentum being its mass times its velocity. So if we try and use light to measure the position and momentum of an electron, so we have an electron that is maybe moving. If we shine light at it, we know that the electron can absorb the radiation and change its energy, and also because of the relative scales of the photon and the electron, this could also deflect where the electron is going, but we have no way to tell. So if we observe the light that comes off of it, whichever way it was traveling to begin with, isn't necessarily going to be its direction that it was traveling afterward. So for an electron, we cannot measure both its momentum and its position. To formalize this, the position, if we define as x, and its momentum with this p, we cannot do it simultaneously for an electron. The equation for the position and the momentum of an electron is given by delta x, so the error in the position, so how certain we know its position, times how certain we know its momentum, has to be greater than or equal to Planck's constant divided by 4 pi. You'll see in many of these chemistry problems we'll still have the delta x for the position. For delta p, this is the same as the change in the mass times the velocity. And so if one of these is constant, so like for an electron we expect it to have a constant mass, we can actually pull that out and it would be the mass times the uncertainty in the velocity. But either way, this has to be greater, this product, than h divided by 4 pi. What this means in practice is that when we are talking about electrons in the quantum model, so the Bohr model, we say they're orbiting, but in the quantum model, we've said that they occupy these orbitals. We can't actually say exactly where they are. We can't say the position and the momentum, but what we can do is give the probability that the electron is in a given location. And this probability is directly related to the wave function. Specifically, it's the wave function squared. So by squaring these wave functions and putting it into 3D space, we can actually determine the shape of orbitals. Let's look at some examples. So if L equals 0, remember this is the second or angular momentum quantum number, and L equals 0 corresponds to s orbitals. And since L equals 0, m sub L can also only equal 0. So there's only going to be one orientation of s orbitals, and they're all going to have a spherical shape. So if we square the wave function, we get a probability distribution that's spherical from the center. Note that these shapes that are often given for the orbitals is actually the shape that contains the electron 90% of the time. So it doesn't mean that there's no chance we'd find the electron out here outside the sphere, but most of the time it's going to be somewhere inside the spherical shape if it is in the L equals 0, m sub L equals 0 orbital. For the p orbitals, this happens when L equals 1. And remember, for L to equal 1, n has to at least equal 2 or higher. So the first p orbitals would be the 2p orbitals. And the p orbitals have sort of a peanut shape. And there's 3 possible values with the m sub L, 0, -1, and +1. So there's 3 possible orientations for the p orbitals. These are defined by the axis that they lie on. So the px orbital would be on the x-axis, the py on the y-axis, and the pz would be the peanut that lied along the z-axis. For the d orbitals, and again these would start at 3d because we'd have L is equal to 2, so n has to equal 3 or greater, and we have the m sub L going from -2 all the way up to +2. And so we have 5 different d orbitals, and for these set, these are defined by the plane that they lie on, so the dxy is going to be in the xy plane, and these sort of have a clover leaf shape. Notice the lobes of the clover leaf for dxy are in between the axes, so there are empty spaces along the axis for the 3dxy, the dxz, which lies in the xz plane, and the dyz, which lies in the yz plane. The other grouping of d orbitals are this dx squared minus y squared, which is in the xy plane, but now the lobes of the clover leaf are on the x and y axis, and the dz squared, which while it has a weird shape is actually analogous to the rest of these orbitals, and it has its main orientation on the z-axis and a donut ring on the xy plane. Following this trend, we have the f orbitals with 7 in total. Again, these will have to start at n equals 4. This is when L equals 3. And so for m sub L, we have these 7 possibilities. And for the f orbitals, you don't really need to worry about the specific shapes of the subgroups. Just remember that there are 7 of them and that these have complicated geometries. And finally, we'll bring up the 4th quantum number, and this is for the electron spin. So it turns out with these orbitals, when we start actually putting the electrons in these probability maps, we can actually fit 2 electrons per orbital because they can have the spin value of either +1/2 or -1/2. If it's +1/2, we call this spin up. -1/2, we call this spin down. It isn't actually spinning in a physical sense. This is just a mathematical term. When we write these, if we're going to write an electron in an energy level, so say this was the 1s orbital, if it has a ms of +1/2, would write it as an upward pointing arrow, and if it's -1/2, would write it as a downward pointing arrow.